Everyone. Welcome back. We are picking up our discussion on recurrent neural networks, and today we will hopefully also meet LSTMs. All right, so here's where we are in this class. We have transitioned from just sort of backing up. We've looked at background and common setup for all of deep learning, computational flow graphs, forward mode, reverse mode, automatic differentiation, gradient descent, what a model class is, what training is, what testing is. We've done all of that. That doesn't change whether you're doing CNNs or RNNs. That is, fundamental building blocks. Then we've sort of looked at how to model visual data, and now we're looking at how to model sequences. And so that's where generally we are in this class. We are picking up on a lot of new terminology. So we're going to be learning about recurrent neural networks, which are a special family within a more broader family of recursive neural networks. Unfortunately, the term RNNs is overloaded. It is used to refer to both a family of models and also a specific instantiation within that family. You can see that logicians were not consulted in naming of these models. Somebody's head would have exploded if they were. So you will see in papers a term called vanilla RNNs, which refers to the specific subclass. Their more formal name is L15 networks. That is what we learned today. And other specifics instantiations are LSTMs and GRUs, which are sub model classes within recurrent neural networks. And we'll teach you backprop through time and truncated backprop through time today. Okay, so we started with this motivation that the reason why we need to introduce a new model family is that we cannot naturally model sequences. Fully connected networks and multi-layer perceptrons in general, feed-forward networks, whether they contain convolution layers or not, cannot naturally model sequences, and they do not handle memory or feedback. And this sort of shows up as soon as you start designing a model, because you commit to a particular input dimensionality and a particular output dimensionality that your network can handle. As soon as different data points start having different dimensionality, we are in trouble because our networks are not designed for that. And so that's the problem that we will deal with today. Sequences may come in different dimensionality based on the input. Some sequences may be long, some will be short. How do we deal with that? So we argued for the fact that sequences are everywhere. There are a bunch of problems that are sequence to sequence problems or sequence tagging problems. So there may be no sequence in the input but sequence in the output. There may be a sequence in the input but no sequence in the output. So for example, sentence classification is a problem where there is a sequence in the input but there's no sequence in the output. There may be sequences in both inputs or outputs, but the structure may be different. So in one, you may be expected to fully absorb one sequence before outputting the other sequence. And in other kinds of problems, you may be asked to output things as the input sequence is coming in. Or there may be a mix and matching happening, that you maybe wait for chunks of the input sequence to come in before you can output something. All of them are on the table. So the way we're going to approach this is, last time we told you that there are two key ideas we will introduce. Instead of just giving you why RNNs or what RNNs are, we will sort of illustrate these two ideas, which are individually useful. But when they come together, a natural solution that emerges is recurrent neural network. And the first key idea is that anytime you have parameter sharing in computational graphs, that results in adding of gradients. And that parameter sharing is a good thing. It can lead to reduction in the number of parameters, and it can, as you'll see, allow you to deal with arbitrary length sequences. So we've already told you sort of understand this, that in a computational flow graph that's represented as a DAG, whenever there are two modules or layers that are sharing a parameter W1 and W2, you can write that down as a third parameter W, and that just results in the partial derivatives with respect to each of these getting added up at this node. The second idea was this notion of unrolling. in computational graphs with parameter sharing. And this is a powerful idea on its own. It does not necessarily need to be coupled with parameter sharing, but it's a powerful idea, which is that some computation graphs may appear to have loops if drawn naively. So if I am trying to say that f is a function that both outputs s and also takes s as input, then it may appear that this computational flow graph has a loop. F has an output that is also its input. However, if I can just index these outputs and inputs with time, if I can just say that there's an st minus 1, which is the input, and st, which is the output, I can unroll this seemingly loopy or cyclic computational flow graph into a cycle-free computational flow graph. By just saying that there is a start state, which is a boundary condition, S0, and then there is a node F theta, and all of these nodes share the same parameter theta. And suddenly this lets us deal with arbitrary length sequences, because it doesn't really matter. I don't have to tell you how many times this state S happens. It can be 1, it can be 10. I can unroll this sequence till arbitrary length sequences without a parameter count blow up, or having a fixed architecture that I need to predetermine to a particular length. So I can suddenly deal with this just by this notion of unrolling. And this notion of unrolling is powerful in its own sake. This is not specifically tied to RNNs. And of course, you can then generalize this. So you could be accepting input at every timestamp. So there can be an xt minus 1, an xt, and an xt plus 1. There can be a computation that you're performing, and that computation is parameterized by an f theta. So there is, in our other sort of notation that we've been saying, there is a parameter here theta, which is the same parameter that goes to all the other nodes. There is a state that we are propagating forward, and this would have been a loopy computational flow graph, but it is not in the way that we are doing this with unrolling. There's a comment, this feels like a Markov chain. Yes, there are natural connections to Markov chains. It's the notion of conditional independence will come in, except you can think of this as like we're going to make the same arguments to Markov blankets and conditional independence, but the exact transition functions are going to be neural networks and learned. Okay, so those are the two ideas: parameter sharing in computational graphs and unrolling. Together, when combined, they allow you to model arbitrary length sequences, and they keep the number of parameters in check. It is not the case that ahead of time you have to define a max length sequence, because you could have said that I have a multi-layer perceptron that deals with a max length sequence, and I will have parameters for each of the slots in this sequence. But we don't have to do that. We don't have this blow up of parameters. Okay. So let me take a question, and then I'll introduce RNNs. But in some applications, the input size can vary. For example, 2 letters followed by 3-letter words, or 2-word sentences followed by 5-word sentence. Then do I dynamically unroll the network to length L? Yes, that's exactly it. You will dynamically unroll depending on the input size. Okay. So here's what a recurrent neural network looks like. So it is a computational flow graph. There is this f theta, which is the computation that we're doing. That computation is recurrent. There's an input we're taking at every time, x, and there is typically an output y that we want to predict at some times. It could be at every point of time you want to predict this output, or it could be only at certain specific times. Let's take the general case where you're predicting this at every time. And one notation that you will hear from us is that we will refer to this as a cell, or a unit of computation that is recurrent. So a recurrent unit of computation. You will often hear the term cell being referred to for that. And you will have a h variable used to refer to the cell hidden representation or cell state. You will hear both terms being used. And what we will do is we will define formally that there will be in old state ht minus 1. So this is the unrolled computational flow graph. It has loops. The output is the input, but you can imagine rolling this out, and we will do this. And what we will do is that for an RNN, we will specify a function f theta fw that takes in the old state ht minus 1, takes in an input xt at some timestamp. At every timestamp t, there will be an x that is the input, y that's the output. We will also define y as some fw2 of ht. We will also have this function, but this is not the tricky part. The recurrence relationship is going to be this relationship, that ht is some function w of ht minus 1 and xt. Okay, and if you think about it, the simplest possible way of constructing this function is matrix multiplication and tanh or sigmoid or ReLU or the kinds of things that we've been seeing in MLPs, right? And that's what we will write this as. And notice the same function and the same set of parameters are used at every timestamp. That is the parameter sharing argument that we've started with. So let's instantiate this function formally. And so the simplest way of writing this function is to basically say that I can take both of these, multiply by matrices, add them with a bias vector, and pass through a nonlinearity. That would be the philosophy of multilayer perceptron. That's everything that we've learned in this class, right? Take ht minus 1, multiply by a matrix whh, take xt minus 1, multiply by a second matrix wxh, and add by a bias bh. You can also read this entire expression as saying that what we are doing is basically we are concatenating ht minus 1. Let me write that without typos. You can also read this as we are concatenating ht minus 1 with xt. We are multiplying by a matrix W, which really has two parts, a WHH part and a WXH part, but really this can be read as a matrix W, and we are adding a bias BH. And this entire thing is being passed through a element-wise nonlinearity to give us this vector. And so HT lives in some dimension, something like 512. This is a choice that we have to make. We have to choose the dimensionality of the hidden state or the hidden cell state. It could be a 512 dimensional vector. It could be a 32 dimensional vector. Basically, we have to decide that HT lives in some R D2 and X lives in some R D1. This typically is application dependent, that X, maybe you have some features coming in, maybe they are one hot vectors for language. And so this D1 usually has a natural choice. D2 is a design choice. We have to decide how many neurons do we want in this choice. Okay, so let me just tell you about how Y is chosen, and then I'll answer a couple of more questions. So this is how we have X as input, H is the hidden state, and we have to, there are two parameter matrices, WHH and WXH. This gives us our H sub T, and typically Y can be the same thing as what you'd like. So if it's a regression problem, it can be a matrix multiplication times HT plus a bias BY. right? So this is a vector, yt can be a vector. If you are trying to perform classification, then you can interpret these as scores for over your classes that can be passed through a softmax. So you can imagine there being an additional sort of softmax layer right after this, or if you're just doing regression, this can be the regressed values directly. So H is the recurrent part, Y is what we're predicting, and we're using the knowledge that we have from constructing multi-layer perceptrons. That's where we are. This is a vanilla recurrent neural network. This is a specific choice for an RNN. This is called a vanilla RNN or an L-man RNN based on the person who proposed it. What makes this L-man RNN? The fact that we chose this particular representation for the recurrent relationship. If we had used a different recurrence relationship, that would not be an L-man neural network. Okay, so let's unroll this out as a computational graph so that we can be a bit more explicit. So there is an F sub W, there is an X1, there's an H0, and this is what people were asking questions of. Typically, this is set to a 0 vector. There is an H1, and we keep unrolling this out. So there's an X2, there's an X3, and so on. This goes out to HT. Capital T is, for this particular example, the length of the sequence, or based on most implementation, actually do have to have some max sequence that they could decode out to. Not all examples have to hit that max, but these are typically for memory considerations, that if the sequence becomes longer than this, we can't handle it. Notice that W is showing up in all of these transformations. And so W can be pulled out as a parameter that we are learning. It's the same weight matrix at every step. If you are making predictions at every step, so if you're making Y1 prediction from H1, Y2 prediction from H2, we will be in the many-to-many case paying losses at every step, computing losses. So recall that if you are, for example, doing, let's say, video classification, so in every frame you're predicting whether there is some activity or not, or let's say in text you're predicting, these are maybe words in a text, and maybe you're predicting a tag for that word. Is this a noun? Is it a verb? Is it an adjective, and so on? So this is a classification problem happening at every time. You have some annotated data for that classification problem, and there's a loss you're computing at every time. So L1, L2, L sub t. And then this is a summation operation that is summing up losses across all times. So now this is the true computational graph that we are optimizing. The objective L is a function of W through all these operations, and we will have to compute the partial of L with respect to W, which means we will have to consider all these paths of dependencies. There are multiple dependency paths that you are seeing in this graph, and we will have to, backprop will have to consider all these paths, because W changes how all of these hidden states are computed, therefore how Y2 is computed, therefore what L2 is, therefore what its contribution to L is. But W also affects how X3 is computed and how Y3 is computed, and so on. Okay. This is the many-to-many and the one-to-many, many-to-one plus one-to-many type sequence-to-sequence model. In this case, what's happening is that we are first encoding this entire X into a particular hidden representation, and then what gets propagated after that is just this hidden representation from which we decode. This comes up in machine translation problems. We can often think of XT as a sequence of words in language 1 and YT to be a sequence of words in language 2. And what happens is that you might want to listen to the entire word before you decode the translation, because there are languages where the ordering of adjective versus nouns is reversed. Which means that if you haven't listened to the entire sentence, you may not know how to translate, because some orderings have to change significantly. So this could be words in language number one. You compress all of that into a single hidden vector, which is sometimes called the meaning vector of this sentence, which is then used to decode with a second set of parameters. So the encoders have one set of parameters and decoders have another set of parameters to get words in language two. So this was what that would look like. So there would be an encoder RNN and a decoder RNN. So when people talk about sequence to sequence, is this the architecture they mean? Yes, absolutely. This is usually the seek-to-seek architecture, but sometimes seek-to-seek is also used to refer to just a generic structure of sequences in, sequences out, but usually this is what they mean. And there's this particular architecture and this particular choice for machine translation was introduced in NeurIPS 14 by Ilya Sutskever and others at Google at the time, and this is that particular architecture. Yeah. Okay. So yeah, a couple of things. Let's take a look at a character level modeling problem, and then we'll look at a couple of other things today. Okay. So let's pick a fairly standard but important problem in NLP called the language modeling problem. And the language modeling problem says, given a data set of text, build an accurate model. So the text is, I give you either sentences or other forms of text. There are Y can represent words or Y can represent characters. Build me an accurate probabilistic model for sequences, P, Y1 through YT. I should be able to give you a sentence and you should be able to tell me, is this an atypical sentence? Is this a typical sentence? And you can also then use this language model to make predictions about the next word in this sequence. Right? And this is what is commonly used in these autocomplete type systems, where as you are typing, looking at the words that you have typed, we can make a prediction for the next word you're going to say. There are parameters in this model. Those parameters can be, in fact, so they can be learned and they can learn things about how grammar of a language is structured, but also how individual users like writing and typing and so on. So that's the goal here. We want to, given a data set of text, which means we've seen many examples of sequences, Y1 through YT, where T is varying for individual sequences, learn a probabilistic model of Y1 through Y capital T. Okay, that's the language modeling problem. And the way we're going to address the language modeling problem is by using RNNs. So let's do this as an example on character level language modeling. By that, what I mean is we are going to not do this at the word level. So every input X T is going to be a character, not a word. And in order to make our figures, or actually, I'll tell you that this is the same as YT in a second, or YT minus 1 in a second, but let's hold that aside for a second. So in order to make the figures work and be manageable, let's assume that our data set contains of only one sequence, which is hello, HELLO. And let's construct a vocabulary, which is the list of characters we are interested in. Typically, this would be our vocabulary would be much larger. We would consider, all 26 characters in the English, in the Latin alphabet, and we would consider some numbers and some special characters and things like that. But let's make our life simple. Let's just consider these 4 characters. So this is the set V, which is the vocabulary. And we are going to, let me erase a couple of things. We're going to say that our input XT is this one hot representation in this vocabulary set, right? So if I want to represent H, I'm just going to put a 1 in the first dimension and zeros everywhere else. If I want to represent E, I'm going to put a 1 in the second dimension and zeros everywhere else, L in the third dimension, And if I had an O, it would have a 1 in the fourth dimension. So, recall that our goal was to learn a probabilistic model, Y1 through Y capital T. We're going to first make an appeal to chain rule. So we're going to say that this probabilistic model is just, PY1 times PY2 given Y1 times, and so many terms given by PYT given Y1 through YT minus 1, and so on. Notice that so far we have not made any assumption. This is true for every single sequence. There have been no assumptions so far. This is just the definition of chain rule and the definition of conditional probability. So the assumption that we're going to make is that this term PYT given Y1 through YT minus 1, that we can approximate this as PYT given HT. That we are going to, this is actually the softmax from an LSTM, which has HT, which is computing HT as an intermediate hidden cell state. So this is the assumption that we're going to be making, and how we're going to fit language modeling or character level language modeling into an RNN structure. So given a particular input E, we're going to compute, which we're interpreting as our input X. We're going to compute HT. So if this is XT at time T, we're going to compute HT at this time, which looks at HT minus 1. From that, we're going to compute this score, and that score over a softmax is going to tell us how to compute these probabilities. So far so good, how we're converting this into a language modeling problem. So this is how we are constructing our language modeling problem and fitting it into this example. And so this is, for example, what that would look like. We have an input character sequence, HELLO. We are converting H into one hot representation. We are doing a matrix multiplication, WXH and W. So we're doing that matrix multiplication. We're adding that bias, and that gives us this, let's say, a three-dimensional. This is X1, this is H1, and H0 was, let's say, the zero vector. And so we're looking at a three-dimensional thing. And this is the operation that we're using to compute this. These numbers then go into a second WHY matrix that is then used to compute these scores. So this is the output layer, and this score can be fed into, so this is, let's say, the score at time T, and you can feed that into a softmax to get probabilities. And so right now, the scores are not very calibrated, right? So the scores right now are saying that the score for the fourth character is the highest, which is the O character. And so after H, this is predicting that at the next time it should be E. And notice that, this is X1, this is X2, this is Y1, which, and notice that X2 is really just Y1. So we are, so Y1 is really just X2. So we are dealing with, this is an auto-encoding type of, or auto-regressive type of a model, where the output for the model is really just the input at the next time, right? So the true output that we'd want from this model, so YGT1 is really X2. And I should write GT here as well. Yeah. So what we want what we want to predict at the first time step is what the next character will be, which is E, and that's why there's an index offset. Right now, the setting of weights is not a very good setting, because you can see that after H, it predicts O to be the highest score. After HE, it predicts the highest score value to be O again. After HEL, in this time, the highest score value is L. So that part is okay, but but so on. So you can see that there are other values that we like. Here is what in green, we are showing what we actually like to have the highest score. So after H, we want E to be, which is the ground truth, to have the highest score. So that's what we've shown in green in these boxes. H, so that's the E, this is the L, L, O. And so we are going to do gradient descent and optimize these losses till the character has the right character that we want in the next timestamp has the highest probability, or we minimize its cross entropy. Okay, let me say one more thing before I get to, So one thing I want you to pay special attention to is this matrix, which is the WXH matrix, which multiplies XT. So let's just pay attention to that. In our example, XT is R to the 4, and HT is R to the 3, right? This is what we're doing in this example. So this matrix, WXH matrix, is a 3 cross 4 matrix. So far so good. It's just a matrix that we are using to multiply with this one hot vector, which is xt, which is 0, 1, 0, 0. There's a 4-dimensional thing which is one hot somewhere else, one hot in one of the coordinates. Now, if you think about this particular matrix vector product, what's happening is that there are columns. There are 4 columns of this matrix. This matrix vector product, what it's really doing is it's pulling out one of the columns, right? Because 0, 1, 0, 0. That product gets multiplied like this. Because X is always one hot, this matrix vector product always corresponds to picking one of the columns of this matrix. And so this first, or the subcomponent of this matrix is really what is known as a character embedding matrix. Because if you think about it, this matrix is giving you, it always has the same number of columns as the vocabulary, and this matrix is telling you how each character is embedded into a dense vector space, that dense space being 3-dimensional space in this case. So this is known as a character embedding matrix. Each one of those columns is known as a character embedding that is then combined with a hidden representation by matrix multiplication and summation as well. And this character embedding is, if you recall, an example from the first lecture in this class, is a way of converting local representations into distributed representations. Local representations are these one-hot representations that take something sophisticated. So imagine, A, B, C, D, those were the characters, and we were just storing one-hot values. The dense representations, the H sub T values, are these dense representations which the W matrix is giving us. Those dense representations will have high values somewhere, low values somewhere else. We do not know what the columns of those, or the rows in our case, of the W matrix mean, or the columns of H mean, but we know that we are going from this one-hot representation to a dense character representation. So that's the connection to something that we've seen earlier in the class. So this is the problem that we talked about, and so this is character level language modeling, and let's now quickly see that we're going to train this with cross entropy. So we're going to do, we're going to have a target character here, a target character here. These targets and these score layers are going to define L sub 1, L sub 2, L sub 3, L sub 4. Each one of these L sub i's is negative log probability of y gt at time t given ht, comma, all the parameters w that we're defining. We will sum up, sorry, let me write that clearly. So ht, comma, all the W parameters. So I'm not indexing the W matrices. I'm not saying HY. So all the W parameters and the biases. So that is, this is L sub T. This summed over all times sub T is your total loss. And this is what you're minimizing over W. So we will we will compute gradients, and we will take the derivative with respect to those gradients. One thing I want you to notice is that during training time, you are always provided, so you're always conditioned on the true input that, x2 is really equal to y gt1, that x3 is equal to y gt2, and so on. This is always true during training time. But this cannot obviously be true during test time, because at test time, you're asked to generate your own sequences. This train test disparity it makes sense from a maximum likelihood perspective or learning perspective. In deep learning land, you will often hear this term teacher forcing, which is this idea that during training, you do not get to take your own predictions. So let's say at the current setting of W that you have, your model wants to predict an O, but it doesn't really matter what your model wants to predict. The X sub 2 is fed to you is YGT1. This is this informal understanding of what a teacher is supposed to do, which is keep correcting your mistakes and keep feeding you the next answer. I disagree with that interpretation. I think that's too pedantic an understanding of what a teacher is for. But in any case, you will hear this term in deep learning literature, teacher forcing. What that really is saying is maximum likelihood estimation, that if you apply maximum likelihood estimation on a sequence model, you will of course get that you condition, P y1 through y capital T will be written down as a product of P yt given y1 through yt minus 1 at all times t's. And clearly this is the true sequence during training. And so we're just doing maximum likelihood estimation, which is the same as minimum of the cross entropy. At test time, though, we have a few different choices. We can do sampling, we can do argmax, or we can do something called beam search. I will show you sampling first, and I'll show you what that looks like, and we'll show you beam search in a second, towards the end of the class. And what sampling really looks like is that you take your first character. Let's say this is what the user has typed, or if the user hasn't typed anything, you could have an encoding of the null character. There's nothing that's been typed. You compute h sub t or h1. You compute the score s1 for each of the 4 characters. And then you pass them through a softmax. These scores are now giving you probabilities, and then you sample a character. So this is y hat 1, which is the result of sampling, not approximation. Let me say it's a result of sampling from the softmax of ht. Softmax, which is the consequence of ht passing through of st. Let me make that clear. Softmax of st. Okay. And so now that softmax, that E, so let's say E gets sampled and that gets passed here. Notice that this E is a pretty rare phenomena. Like there was only a 13% chance that we would sample an E. And so it's more likely that we could have sampled an O. But let's say an E gets sampled, you feed that E now as input. You convert that into one hot representation. You feed that as input. You pass this forward. You compute an H. You compute a score. You compute these probabilities again. Now there's 25% chance an H will get sampled. There's a 50% chance that an O gets sampled, and we continue on. Notice that, I'm saying that HELLO is getting sampled, but it's very likely if I had taken an argmax, what would have gotten, so an argmax you don't sample. If I had done an argmax, what would have come here would have been O, and then we don't know what these probabilities are going to be because they are conditioned on E, but it's very clear that we would have headed down a different trajectory in this sequence. We would have ended up with H, O, and then whatever this leads to, we would have sampled a different sequence. So that was a character level language modeling, and there were questions about how do we train this. Well, remember that if you are, the algorithm for training this is, or the algorithm for computing the gradients is backpropagation, and we refer to backpropagation applied on an unrolled computational flow graph corresponding to an RNN as backpropagation through time. These are all the X1s, X2s to X capital T's. So given a sequence, you will unroll it to its full length. You will compute all the hidden values. You will compute all the Y1s through YTs. You will compute L1s and so on. All of them will get summed together. And the final thing will give you the total loss. And you will compute the gradient of the loss with respect to the parameters. And you will take a step in the negative gradient direction. One of the immediate problems that we run into with RNNs is that sometimes our sequences are so long that there's no way we can actually do backpropagation for the entire sequence, that it would be too slow and it would be too memory inefficient. By that, what I mean is consider this character level language modeling problem that I just talked about. Consider doing that on all of Wikipedia text. Now, you have to first pick what is my sequence. Like, what if the entire Wikipedia book corpus, like what if an entire Wikipedia page, including the periods and the spaces and the, the headings and everything, is one sequence? Those are massively long sequences, and you would have to, forward prop through an entire page of Wikipedia before you can compute the losses for this really long sequence before you, and then you can do one step of backprop, and then you'd have to forward prop again. So it can be, for long sequences, it can be really inefficient because you have a lot of forward passes involved before you can take one backward pass step. And so there is an algorithm called truncated backpropagation through time, which is a heuristic algorithm where you basically define a backpropagation window, a Tmax, if you will. You can handle sequences longer than Tmax, but so think of it as backpropagation through time parameter Tmax. And so you define a temporal window. You go from X1 through X Tmax, if you will. You forward prop only till that sequence. You compute losses. You compute gradients in this, given this loss. You take a step in the direction of the negative gradient, and then you essentially move the window forward, propagate the H T maxes over. So this is the key step. So the H T maxes are not being reset at window boundaries to 0. They are still being propagated over, but now it is X T max to X 2 times T max that we are forward propping over, computing losses only within this window, and then doing backprop only within this window, so stopping at the boundary of window. So we're carrying the hidden states forward in time forever, but only backpropagating to some smaller number of steps. So this is an intermediate thing that we are not actually breaking our sequences into chunks of Tmax. It is not that after Tmax we forget that we were in the middle of a sequence. We are propagating H Tmax over at every window boundary, but backpropagation is truncated through time. And so this is just a heuristic algorithm. It is very common in implementations to make sure that we can actually run this efficiently. It naturally limits the kinds of dependencies that we can pick up, because you cannot actually adjust parameters beyond the truncation window. You don't have to pay costs. You don't have to deal with the gradients beyond the truncation window. But it's an important algorithm needed for actually training these models. Okay, and you would propagate that forward in time. Could you explain the reason for truncated backprop through time? What's the intuition behind it? Well, the reason is efficiency. That if, for example, you're doing, as I said, character modeling on all of Wikipedia, that the sequence X1 through X capital T is an entire page, Wikipedia page text, then for every backprop step, you're having to forward prop this entire sequence. That would be too slow, and we would have to hold all of these intermediate hidden activations in memory. So efficiency, both computational and memory budget, force us to deal with this heuristic. Is it possible for that time window to just be one step? It's generally not common, and it's not common because you generally have more memory than that, and it's not that slow to forward prop. So these backward through time windows, so typically you're in the, maybe sequence lengths of 128, 256, 512, 1,000 length sequences I've seen being tried. If you're in that window, depending on your batch size, maybe your sequence length is 32 or 64. Those are much more common sizes. One is typically not common unless there's something specific about your problem that you really cannot handle. And at that point, it's really questionable how much benefit you will get from a recurrent model. Yes, of course, the hidden states are being propagated forward, but if the gradients are getting clipped at every point of time, it's really questionable how much sequence modeling you're really doing. Does truncated backprop equivalent to non-truncated? So how much error? It is not equivalent to non-truncated. How much error does it introduce? That's a computational question. How do we quantify it? That's pretty easy. How would you quantify it? You take a sequence which is short enough that your memory budget allows you to do non-truncated backprop through time, and then you compare it to truncated backprop through time in that system and see how much error it introduces. So that comparison is pretty easy, and that's how we would quantify it, both in terms of training error and testing error. How is storage requirement less for truncated backprop? Don't we have to store X and HT for the entire sequence? Yes, but not in the same batch, right? So not at the same time. In truncated backprop through time, I have these three windows. At any given point of time, I just have to store H1 and H2, HT max and X's for this window. When I move to the next window, this part of the sequence can be entirely dropped. I don't have to store H1s through HT max because I just have to carry over HT, and then I only have to store these activations and windows in the activations and inputs in the next window. So the storage requirement is less because I do not have to store the entire sequence. I only have to store the subset of the sequence in memory. Okay. Oh, and these are fun examples. So this is a really fun set of experiments that Justin Johnson and Andre Karpathy did at Stanford. This is a famous paper that famously got rejected. It did not get accepted at ICLR, I think the year they submitted it, but this was just a fun set of experiments. It was annoying and sad that reviewers did not find value in this. I thought this was a wonderful paper. So they did these experiments where they trained character level language models on Shakespeare sonnets, on other sorts of data. And so notice that this is character level language model, right? So the characters are 26 characters plus special characters, capitalized, non-capitalized, everything, spaces, new lines, those are all characters in your vocabulary. And so this is, for example, the kinds of characters that your models are producing. So notice it produces a T, Y, N, there's a hyphen in there, there's a space character, and so on. So the first thing that the model isn't even learning early on in the training are that you typically don't have two spaces right after another, commas don't have spaces before them, and so on. You train some more and notice that, things start to become much more like a sentence, that there is a new line, there's a full stop that doesn't have space before, there's a full stop that has a space after it. The words don't really make sense yet. THOM is not really a word. Here, at least, is a word. Quotes are open and quotes are closed. That's good. But after a while, these things start looking like real sentences. There's a quote opened. Why do what that day? Okay, so that's not a meaningful question, but it is a question. The comma is inside the quote. Oh, that's nice. Rules of, pedantic rules of grammar respected. Replied Natasha, and wishing to himself the fact that Princess Mary was easy, fed in that they offered him, and so on. I have no idea what this sentence means, but at least it sounds like a sentence. And they're able to generate what look like essentially plays, right? So there is a capitalized character name, there's a colon, there's a new line character, alas, I think he shall become approached and the other day, and so on. And notice that this is a fairly long sequence. It's a fairly long sequence because we are doing character level modeling. But the model is picking up on the fact that there are these, you have to have name things and then what they say, because those are the sequences it is exposed to. There are things that sound like poems that get emitted. So these are generated sequences from the model. They also then took the LaTeX source for an algebraic geometry textbook. So just raw LaTeX. This is not PDF, but with all commands and everything. And so this is generated text in from their sequence model. It's generating symbols with subscripts, superscripts, with what looks like what you might expect in a math textbooks. For this symbol where L is equal to 0, we can find a closed subset H in H. Well, this one's kind of long. There's a mathcal H in H that doesn't make any sense. Proof of one, there's a theorem, there's a proof. There's a very nice proof that says see discussions of sheaves of sets. So the proof is actually not done here. There is a QED character at the end of a proof at various places. And notice there's a lemma which is 0.1. So there's some numbering of lemmas that is consistent across these things. So this is a long sequence being generated with the structure of the data coming out as what the model has learned. There are some cases where the RNN decides to emit the proof, which I think is pretty funny. There are places where if you've done LaTeX, you know that there are diagrams in LaTeX that can be constructed purely from commands that can be typed out. So the model is actually trying to generate some diagrams in the proofs. And I think when I read this paper, their claims were that this is largely compilable. So LaTeX is a programming sort of language, right? You can have errors in that, and so this was largely compilable. They had to fix a few errors, but that in itself suggests that the grammar of the language was learned by the model. And then they took all of the Linux source code on GitHub, just fed an entire C function. And notice this is generated C code now. Again, this is character level modeling, right? So you first have to learn that there is static a word with a space. So static void do command. There's a function that this model generate which takes in a struct, which is a sequence file, which is pointer. The sequence file has to be defined somewhere else anyway. A void pointer. The model decides to have a column, which is it defines variables. One problem that they describe that it often does is so it figures out that there are iterators and it consistently uses those iterators. That's fine, but it ends up defining variables that it never uses anywhere else in the system, and sometimes it does use variables that weren't defined anywhere else. It learns to recite the entire header and the copyright terms of notice at the top of the things. And notice again, this is all character level modeling, right? You have a slash, asterisk, new line, and so on, and so it recites the entire copyright header because that gives it lots of negative loss. You can drop your losses very easily because every time there is a first character symbol, you know what has to come after it are these particular characters, because the first part of your sequences are extremely predictable. You know what these sequences should be. Then there's a bunch of includes that come and so on. So this is a fun set of experiments. I encourage you to take a look at this particular paper to read these experiments. This is a very, very fun set of experiments.